Hi everyone, today I wanted to post another video where we can talk more about trees. You might have been wondering where I've been for the last few months. The last video I posted I was sort of finishing up in the final stages of my PhD, and now that I've finished my PhD and moved on to a postdoc research job, I've been quite busy with that. But from today on I wanted to start posting videos on a regular basis again, and I thought I'd pick up where we left off. We'll talk more about trees. So if you don't really remember what a tree is, it might be helpful to go to the previous video, which was video 36, and see what a tree is. For example, we may have three vertices and connect them up with a couple of edges and maybe tack on another guy like this and another guy like this, but make sure that we never make a cycle and we never become disconnected. And then we have a tree. So what I want to do is talk a little bit about some cool facts about trees, and we'll see how nice they are in general. So the first little fact that I want to show you is that in fact a graph G is a tree if and only if it happens to be acyclic, which means doesn't have a cycle, and the number of edges in the graph is equal to the number of vertices minus 1. And if you remember the basics from the definition of a tree, you'll think, wait a minute, that sounds really familiar. Isn't a tree something that's just acyclic and connected? You're right. A tree is something that is acyclic and connected. That's the definition. So we'll keep that in mind. And now we have to worry about this condition over here and see what we can do. Now, a lot of the time in a graph, we'll call the number of edges m and the number of vertices n. So this is like saying m equals n minus 1. And sometimes I'll do that in this video just because all of this notation gets a little bit in the way. So let's start to think, how would we prove this theorem? Well, it's an if and only if theorem, so let's start with one direction. Let's start with the direction where we suppose that the graph is a tree. So let's say that G is a tree, and we're going to want to prove that it is acyclic and has m equal to n minus 1. Well, hold on. G is a tree, so by definition, it's acyclic. Great, that part's easy. So by definition, we have acyclic. Yay, this is the definition. Awesome. What else do we need to do? Well, we know G is a tree, and therefore we know it's acyclic and connected, and all we need to do is to show that m is equal to n minus 1. Well, the way we're going to do that is actually by induction. And if you don't remember induction or you're not familiar with it, I advise you to go back to video 15 where we talk about the basics of induction. So here we're going to be using induction on n. So when we do that, we have to worry about our base case. And our base case is really just when n equals 1. That's the smallest possible tree we could consider. And what does it look like? Well, it's really boring. It's just a single vertex with absolutely no edges. Well, what does that mean? It means that the number of edges is 0, and that's good, because that literally means we've satisfied this. M is equal to n minus 1 in this very, very trivial case. Excellent. So our base case is covered. Now we need to write out what is our induction hypothesis. I usually write ind-hyp or IH depending. And here is our induction hypothesis. Suppose all trees of order n, remember order n just means that have n vertices. Suppose they all have n minus 1 edges. And this is something that we suppose for some n which is bigger than or equal to 1. We already know that it's true in the n equals 1 case. So now we suppose it's true for some n, and our next big step, the whole point of this proof, is to show that this is going to be true for n plus 1. So what we have to do right now is say let T be a tree of order n plus 1. And what we need to do is just use this inductive hypothesis to show that the theorem will hold also for this tree of order n plus 1. Okay, so we have some tree. It's called T. It has n plus 1 vertices. There's a bunch of them. I'm just drawing some random vertices. We don't know how they're connected. They're connected via some way. We don't know what it looks like. But we do know one thing. In the first video we had about trees, video 36, we mentioned that every tree has to have at least 2 leaves. Remember that a leaf vertex is something like this of degree 1. So we know that there exists, this symbol means there exists, at least 2 leaves. That's good. So there exists at least 2. All we need is one of them. We're going to say let V be a vertex of our tree with degree 1. With degree 1, i.e. it's a leaf. So here we are. This is some leaf. And maybe this is our picture. It has some huge number of vertices, and this is our little V. Okay, fine. Now what we're going to do is we're going to say that we are looking at a smaller tree, but just barely smaller. We're going to look at a tree which we're going to call T prime, and it's going to be everything that T had except not V, and of course not the edge that V was on. So we're going to let T prime be our original T without V, and we look at this T prime. Okay, well, what does T prime have? How many vertices does it have? Well, all we did was remove a single vertex, so it's got to have n vertices. And we have this lovely induction hypothesis right here that says all trees of order n are going to have n minus 1 edges. So we know, therefore, T prime has n minus 1 edges. Excellent. Well, I hope you can see what we're going to do now. Maybe you want to pause the video and think about it. All we have to say is, therefore, T has n minus 1 plus 1 edges. Why is that? Well, it has the same edges that T prime had, plus this single one here that was associated with the V. Well, how many edges is that? That's n edges. So this is equal to n edges. But it had order n plus 1. So we've just shown that the number of edges this tree T has, is equal to the number of vertices minus 1. Great. So take a moment, make sure that's clear, but we've basically just done the first part. We said that if a graph is a tree, then obviously it's acyclic, that's part of the definition, and we were able to show that the number of edges it has is equal to the number of vertices minus 1. Excellent. First part done. Second part to go. Let's scroll down a little bit and remember what we're going to be doing. We are going to take a graph which is acyclic and has m equal to n minus 1, and we're going to try to show that that is a tree. So let's just scroll down here and get ready to do that portion of the proof. Okay, so we're going to say suppose G is acyclic, and m, which is the number of edges, is equal to n minus 1, the number of vertices minus 1. So if our goal right now is to show that G is a tree, all we need to do is to show that G is connected. All right, so let's give ourselves a bit of space to do this. Remember that at the moment, we don't know that G is connected. That's what we're trying to show. So all we can really say is, well, maybe it's not connected, but it certainly will have connected components. If you don't remember what connected components are, I suggest you look at video number 17 where we talk about them. So let's say that it has some connected components. I'm going to draw them as these blobs. They do not have to have the same size at all. A bunch of blobs. Maybe this one is G1 and G2, and then there's a bunch of them. I'll just call this one GI for some intermediate blob, and there's a bunch of them, and maybe we have K blobs. Let me write that more clearly. That's a K. So we have these K connected components, and what I want to do is say, well, let's look at each one of these connecting components and say how many vertices and how many edges they have. Well, we don't know, so we're just going to call them something like N1 and M1 for this component. N being the number of vertices that are here, and M being the number of edges that are here. So in general, we'll have Ni vertices and Mi edges inside of one of these components. And now I'd like you to think very carefully about a single component GI. What do we know about this component? Well, it has Ni vertices and Mi edges. Fine. It's acyclic, and oh, it's connected because it's by definition one of these connected components. So that's great. This GI happens to be acyclic. Why is it acyclic? Well, the whole graph is acyclic, so there certainly cannot be a cycle in one of the components. So it's acyclic, but it's also a connected component. It's also connected. So by very definition, we know that GI, this component, is a tree. Okay, that's excellent. Why is that excellent? Well, it's because in the very first part of the proof, we've already shown that any tree must have number of edges equal to the number of vertices minus 1. What does that mean? It means that number of edges, mi, must be equal to the number of vertices, ni, minus 1. Now that might not look very significant at the moment, but this is true for each one of these components. They're each connected and acyclic, so they each satisfy exactly this. Let's figure out how this information will help us. Let's think about our original graph G, the thing that uses up every bit of information up here. So it's all of these pieces. Well, if G has m edges, really m is just the sum of m1, m2, m3, mi, all the way up to mk, right? So we know that m, the number of edges in the total, is just equal to the sum of all of these mi's, where I goes from 1 up to k. But we also know that each individual mi can be written as an individual ni, where I goes from 1 to k. My k keeps looking funny. There we go. Where mi is always ni minus 1. Well, why is that useful? It's really useful because we know now that this is just n minus k. Think about why that is. If you think about G, the whole graph, it simply has n vertices, which come from these vertices plus these vertices plus these plus all of these, right? So the number of vertices n is equal to the sum of the ni's. And when you subtract off 1 k times, that's where you get this minus k. All right, so we have m equals n minus k. Aha. We also know from up top that m is equal to n minus 1. So what does this mean? It means that n minus 1 must equal n minus k. Now I hope you see where we've been going with this. This means that k must equal 1. And if k equals 1, that means that really, in reality, there was only ever one connected component. So this means that there was only one connected component. And what does that mean? It means the graph was connected. So G was acyclic and it was connected. So that means that G is a tree. Excellent. That means that we have completed the proof. I'll just scroll back up so you can see the statement of what we proved. We've proved that a graph is a tree if and only if it is acyclic and the number of edges is equal to the number of vertices minus 1. Ta-da! Hope you had fun.